and I think we will get started, and then we will let people in the room as we come along. So once again, my name is Madeleine. I would like to welcome you to this webinar with the topic Electrification Demands Reliable Electric Contacts. And it's the 22nd webinar in our series. And we can take the next one. And as you see, we have a big group of people, and we are really happy to see a lot of you from many companies, and I think we have 6 or 7 different countries here today. So most welcome. And also we'd like to say before we start some words about our project, the WebLearn project. If you take the next slide, Peter. Our project, we have been doing this for a while now, and our aim is, of course, to provide and support competence for industry within this topic, metal and polymer in component manufacturing. And I would like to just share how many we have had. This is the 22nd webinar. We have so far had over 800 registered participants and also 51 countries or 51 nationalities. So we are very happy for that. So good, and we will continue for some more time. And hosts today, it's me and Madeleine Zetterlind. If you see the next slide there, Peter. And then I will soon leave the floor to Katarina. Please, you will be the moderator.
I will be your moderator for today's presentation and discussion. And if we take the next slide, I'm going to introduce you our speakers. I'm very happy to welcome Anders Skalski, that is the VD of Provexa Technology. Together with him will be our Professor Peter Leisner at the Department of Materials and Manufacturing at the School of Engineering here in Jönköping. I'm very glad, and if we take the next slide, I would like only to give you a little bit of instruction for today. We start with the agenda. We are doing the introduction with a little bit instruction at the moment, and then we will have presentation. After the presentation of about 1 hour, we would like to invite you for a panel discussion where we can ask different questions and we can learn more from our presenter. At 11:30, we plan to wrap up and close the webinar. Next slide, please. Please keep your microphone turned off during the presentation, and you are welcome to turn it on when it's question time. Questions can be collected through the chat during the presentation, so we can ask them at the end of this part. And when we do the group discussion, we think this is very important to get your feedback and also to give you a little bit more insight. We consider this part really important, so we can have your input as well. Our webinars are recorded only in the presentation part, so keep your camera off if you do not want to be part of the video. We will turn off the recording during the discussion, so that part is more informal. Please, if you can take the next one. We are probably very familiar nowadays with all these remote tools, but just a small reminder about Zoom interface. You get a bottom bar with all these functions. The first function is to open and close your mic.
We can't hear you. Katarina, I think your sound disappeared.
Can you say something, Katarina, or should we just move on?
I think should we move on? I don't know how we lost her sound.
Something happened here. We can just say with this picture, you can write in the chat and if you have questions, and you see also where you mute and unmute your camera. I think everyone knows this. So I think we can move on. So we see something happened. And then I will introduce you, Peter.
Thank you.
Now we will start the webinar, and so the floor is yours.
Thank you, and good morning, everyone. The title of this webinar is Electrification Demands Reliable Electrical Contacts. And why we have chosen this subject is that electrification is a mega trend in the society. So more and more products are becoming electric powered, but it's not just about electric power. Also more components or products are becoming connected. And we will see products who we in the past considered as purely mechanical products are becoming more and more smart and electrified as automated products. And one important component among many others in such products are electric contacts. You might consider it as a simple product, but maybe we can convince you during the day that there are actually many demands on electric contacts. They're used in many different environments. And as you can see on these pictures here, we have, for example, the ferry, which is in offshore environment all year round, and like many wind power stations that are also placed offshore. So you will have electric contacts from the very low end, like if you see the example here, thermocouple from our own laboratory, there we want to measure microvolts with high precision, and we in principle have no current flowing. And then we have some items which all of us use every day, smart cards, UPS, a few volts, tens to hundreds of millivolts. And in the completely other end of the scale, we have electric power switches handling hundreds of volts, thousands of amps. So it's of course very different demands we have of these different contacts. And they are used both for power transfer, but we also have these signal transfer contacts handling complex signals. And again, we're using them in very different environments, and they should survive their lifetime in that. So what is an electric contact? It is an electric contact is a junction where you can carry electric current. And it consists of two parts which you put together, but you should also be able to release them again. So it's not a soldering, it's not a welding. It should be able to take them apart. So it consists of these two contact members. And if you, at least if you work with direct current, you can talk about an anode and a cathode, which is put together. But the whole setup is rather complex because you have two interacting bodies. You have an mechanical environment because you're pressing them together. You have an electric environment. You have a thermal environment, especially in the contact area. And you also have a chemical environment, depending on where you're using your contact. And all these different environments need to be satisfied in your design of your contact. So if we go into more details and look how it looks in micro scale on the surface of the contact, it might look flat, but if you really zoom in, you will see something like what you see here. It will be micro rough, and you will have something on the surface. If it's non-precious metals, you have an oxide film, and even on precious metals like gold, you will have some surface contamination from the surrounding on the surface. So when you press it together, as you see on B, then you start to have the mechanical contact. It will be pressed, and you will have islands, which will be the load carrying area. But when you still have surface contaminants or oxide films, the current will not flow through the whole mechanical contact area. There will be in even smaller spots, which we call usually A spots, which is the conducting area. Illustrated as see here that you'll have the whole apparent contact surface, you will have islands where you have mechanical contact, and then you have even smaller islands where you have the real electric contact. And since it's narrowing down in the electric contact, you will have electric resistance. And you can see on the microscopic picture here on the other side, a picture of a real contact. You can see there are micro roughnesses on the surface. And a little more on this, we will have what we call A spots, where the real current is actually flowing between the two areas, which is a much smaller area than the whole contact. And if you want to increase the load bearing area, we have this relationship here. So the area will grow if you increase the force, the contact force, then you press it more together. But if the hardness of your material, the softest material in your contact, is increased, then you will decrease the area. So there's a relationship between the area and the force and the hardness of the materials. And the same thing will also affect these A spot, the conducting area. And this is illustrated to the right, where we have the contact resistance on a logarithmic scale as a function of the contact force. And here we can see for 3 different materials that it drops when you increase the force. And it drops a lot actually in the beginning because it's a logarithmic scale. So now I want to introduce a phenomenon called fritting, which should not be mixed up with something called fretting, which I will come back to later. So now we're talking about fritting, spelled with an I. And this is the destruction of insulating oxide layers by a voltage gradient. So for materials which has an oxide film, if the oxide film is intact, there will be a high resistance. And therefore you can, typically you will say you will be able to grow a gradient over an oxide film which is 10 to the power of 8 volts per meter. And if I have to translate that into something more relevant for the scale of contacts, that means 5 volts for 50 nanometer of oxide, which is needed for breaking down the oxide film. And this also means that in ordinary household contacts, like you see them here to the right, which are made of copper alloys or maybe nickel-coated copper alloys, there it's quite normal that you use 1 or several volts to break down the oxide film. And that's of course no problem when you have 240 volts in the system. And this is also illustrated on the curve. Here we have the contact resistance again in a logarithmic scale as a function of the voltage over the contact, also on a logarithmic scale. And at low voltages, the resistance is very high until you have the breakthrough voltage around 1 volt. And then it becomes constantly low for a big range of voltages. I will now introduce 3 types of electric contacts, and that is stationary contacts, sliding contacts, and switching contacts. So a stationary contact is a contact which is in its function supposed to be stationary, to be mounted and not released in usual cases, but it should be releasable, for example, during service and maintenance, but during the lifetime, it will probably only be released a very few times. And that could be for some parts sitting under the hood in your car, for example. It will sit there for maybe some years, and then you need to change something, and then it's screwed loose, and then it's mounted again afterwards. So this is one type of contacts. A completely different type of contacts is sliding contacts. Here you have a situation where you have electric contact when you're doing the sliding. So you have a situation where there is a risk of wear. And the stationary part is pressed against the rotating part. And the higher the contact force is, the higher the mechanical wear will be. But on the other hand, if you try to release the contact force, there is the risk that you now and then will lose electric contact and you will have arcing. And these electric sparks will also wear the surface. And that will be a lot if you have too low contact force. So in design of such contacts, it's important to find the minimum total wear as is illustrated in the diagram in the middle. We have the mechanical wear growing linearly with the force of the contact, but we have the electric wear due to arcing growing a lot if you have low force. And somewhere there will be a minimum which will give less wear to the contact system. To the right, you see an example of a rotating contact from a wind power station. And then we have switching contacts or plug-in contacts. And their function is to be switched on and be switched off. So that will happen many times during the lifetime of the contact. So again here, wear is of course an issue, and the mechanical wear could be both adhesive or abrasive. Arcing could also happen for this type of contacts. If you plug out a device at home in your 240 volt system and the light is off, then you will actually be able to see sparks as well. And this means also this arcing could also evaporate and transfer material between the contact bodies. You might also in A spots have the risk of micro melting, which is creating bridges between the materials, which is broken again. So that is also a type of wear. And then we have what is called fretting, which I will come to on the next slide. So the challenge is always here depending on the application to find the right design, the right material properties, the right material combinations to minimize wear and to have a long lifetime that matches the product. So the phenomenon fretting wear, fretting is always associated to vibration, meaning that you will have small oscillating motions between the two contact bodies. And the amplitude could be in the size of micrometers or up to millimeters. And this could usually related to machinery, car, or airplanes, where you know you have vibrations. And this is tested on vibrators. So this is from a test lab where you an electronic module is vibrated, supposed to see that components are actually staying where they should stay, but you will also be able to find out if you have wear problems or contact problems due to fretting wear. And the mechanism could be that you have micro welding, which will lead to adhesive wear. And then you can say, okay, how do we avoid this type of wear? The best thing is, of course, if you can change your design so you don't have vibrations where you have your contact, but it is easier to say than to solve in reality. Then again, you can lower your contact load. Then you have lower mechanical force, or you can increase the hardness of the materials in the contact bodies. On the picture, lower picture to the right, you will see an X-ray photo of an electronic contact, male-female contact. And you can imagine if this is vibrating, that it's easy to have damages just in the contact area. And another example related to fretting is that you might have material which is loosened from the surface of the contact pair, which results in debris, which will lie in between the contacts. This itself will increase the electric resistance, but if it's, for example, is particles from nickel or tin, it will form hard oxides, which will actually increase the wear of the two surfaces. Stable combinations is considered to be gold against gold and silver against gold. There you have precious metals that do not form oxides. So another example of material combination is where you have a soft coating against a relatively hard coating. And in this example here, we will have tin, which is very soft, 40 vigors, against hard gold. And hard gold is gold which is alloyed to be harder, in this case 200 vigors. And if these two are in contact, the tin will smear out on the hard gold surface and creating a very thin layer on the hard gold. And tin will form an oxide film. So on the gold coating, you will actually have a sandwich with hard gold, thin, very soft tin, and on top of that, the hard tin oxide. And since the smeared out tin is so soft, or not soft, but so thin, then you cannot really break the oxide, and that will increase the electric resistance. And then, of course, you can say then we increase the contact force, but then there might be a risk that you actually start to have micro welding and alloying between the tin and the gold. So this is not a popular combination. So back to the different possibilities, I want to show you some common contact coatings. Of course, there exist other possibilities, but these are common, and I have in this table also show some pros, some cons, common hardness intervals, and recommended contact force when using these materials. And the first coating is no coating at all. That means we will have copper or copper alloys as the contact material, which is common in household, as already discussed. They will have oxides on the surface. The hardness will differ depending on what type of copper alloy it is and how it's treated. So from soft to middle hard, and you need a high contact force. Then you can use a nickel coating or nickel alloy coating. And again, talking about nickel and nickel alloys, it's a big difference in hardness and properties of these. Anders will come back to this in more details. But these are relatively hard or hard coatings, also oxides, and also need a high contact force if they're used as the top coating. Then we have silver, which is popular for high power contacts or high voltage contacts. It could form sulfides on the surface, not so critical when you have high voltages. It's relatively soft and can only need, let's say, a lower contact force. Then we have tin. It's okay in most cases to have silver as the counterpart. It's due to the softness, it's usually used in situations where you only have few mating cycles, usually what's called the stationary contacts. It's very soft. Then we have palladium or palladium alloys as alternative to gold as a precious coating, forms no oxide film, quite hard, and need a quite low contact force. Pure palladium is a catalytic material, so therefore you might have the risk that pollutants from the air can react on the surface and create contamination. In that case, it could be wise to have a thin gold top layer. If you have the palladium alloys, this risk is less. Then we have different types of gold. We have soft gold, which is pure gold. It is not wear resistant, but in the microelectronics or circuit boards, you might have on the same component both a contact area and then other areas where they want to wire bond or solder component to the surface. So it could be a good combination of that. But else for real switching contact, you would prefer hard gold, that is alloyed gold, which is difficult to solder, but it's harder and you can use it with a low contact force. And the same as for the flash gold used on top. But since it's very thin, it could also be weared away. And on the next slide, we can also see how does it look if you make a cross section and see how does these layers build up. Usually, and you can see we have a scale here to the left showing approximately the thickness of the different coatings. And we have this, let's say, household example with nickel and copper for relatively high voltage, let's say 240. We have the other system for the stationary contacts, who also need some medium to higher voltage and a few matings with tin on top. We have the high voltage contact with silver. There you demand 20 micrometers of silver if it's a thick coating for high quality contacts. If you want a T-band little lower quality contact, you can have an intermediate nickel layer and reduce the thickness of the silver. Then we have for electronics or electronic signals also, copper, nickel or nickel alloy and gold on top. This is, for example, what you will have on your smart card if it's golden. If it's not golden, your smart card, then it's because you have palladium on top. And for normal switching contacts for electronics, low voltage, and for signals, you will have a stack where you have the copper layer in the bottom, nickel, and then hard gold on top. And the alternative to that is the one where you have nickel and a palladium alloy and maybe a flash gold on top, which could be hard gold or soft gold. And something we have not talked about is for sliding contacts. If there are high demands on wear resistance and resistance to arcing, you could use rhodium as a precious metal of high hardness, but also very expensive. So I will end with a small case story, because now we have talked about the technical properties, which is very important for designing a good contact. But for making a solution that is good on the market, we also need to consider what does it cost. And since we talk also about precious metals, there could be a lot of cost involved in this. So this case I will talk about here is an old case. It's from Lucent Technology in the United States, the former AT&T Bell. And back in the 80s and 90s, they wanted to substitute gold with palladium in order to save a lot of costs. But they wanted to maintain the quality. That was very important. And they were actually able to do that. And if you look at this diagram here, we can see during that period, gold was about 3 times more expensive than palladium. So it was good business. It was so good business that during 1995, Lucent Technology saved more than $100 million in costs. And they also got a technology award for this invention. And there was maybe an issue for customer acceptance. Was it really the same quality when it was not gold? But then you could give a flash gold on top. Then it looks exactly the same as the gold contact. And you might even have advantage that you will have less friction and better solderability. Of course, it's an extra cost as well. So this was very good. But what happened then? Oh, a few years after, the price of palladium increased a lot. So suddenly it was the palladium which was 4 times more expensive than gold. And even when you consider that the density of palladium is 60% of gold and calculate the price not as dollars per ounce, but dollars per volume, it will still be more expensive using palladium. So this was not so easy. And what happened further on? Well, for a long period, it went back to the situation that gold was more expensive than palladium. But in the last 2 years, we have a situation where palladium is back as being more expensive again. So we have these critical periods with extra expensive palladium.
Can I ask a question?
Yes, if you give me half a minute, because then I'm finished with my presentation, and then we can take it like that. Let's see how. Oh, I was there actually. Yes, please.
We will start using silver-plated terminals on Husqvarna in the future. How does the silver in this price table? How low is it or high
I
is
think
it?
silver is usually roughly 100 times cheaper than gold.
Yeah.
So from that point of view, you're far away from these curves.
Yeah.
And of course, you can always discuss also how will this develop in future. Who knows? If you have crisis in the world, war and things like that, investors usually turn to gold, and then gold prices goes up. If industries is working very well, you have a high conjuncture, then usually prices on palladium type group metals like palladium, platinum, and so on will increase. And what happens now in electrification? We use today palladium in catalysts for cars with combustion engines. In future, we'll probably use less there. But if you start to use fuel cell cars, then we will use at least palladium group, platinum group metals in that technology. And how much will that be compared to what's used today? That will also affect the price. But this is actually the end of my